Jeremy Goodman, as a professor at Princeton Asbury, and we're talking today about protostellar disks.
Thank you. Thank you for having me. It's always a pleasure, I say that without reservation, to come here. This happens to be my fall break, so I don't have to teach this week. And thank you for the CITA mug. When I first came here, it must have been, could it have been 20 years ago? It's a long time. How old is CITA? 25, yeah, probably was around then. I was given a mug, and then I lost it. When I returned a few years later, and Scott was director, he said, no, one per customer. You don't get another mug. But evidently, you haven't, well, the policies have changed, or you haven't been keeping your records. Now I have another one. All right. So, sorry the title came through so late. I kept expecting someone to prompt me for one, and they never did. So, but here it is. The subject is the implications of dust, I suppose, and molecules in protostellar disks for their emissions on the one hand, which is something that other people know a great deal more about than I do, and their dynamics on the other. And of course, I approach the subject as a dynamicist. But my view of the study of protostellar disks is that you can divide the communities into two parts. Those who worry about explaining the photons that arrive and model the microphysics of the production of those photons and the chemistry and so forth. I should probably make finer distinctions, but I'm lumping them all together. Microphysics types. And then the people who worry about the angular momentum transport and the turbulence and how the disk accretes. I belong to that community usually. And remarkably, there is very little overlap in the literature between these two approaches. But the disk has implications for both. And this is really only the first step in what I hope, if NASA smiles upon me, will be a longer project to try to explore these connections. It's also a lot of what I would have called, before I got involved myself, dirty physics. That is, lots of microphysics involved. So if you press me too hard on, for example, astrochemistry, you will quickly discover the limitations of my knowledge. But it's always exciting to learn new things. So we observe protostellar disks mostly through their dust. I'm sorry this is so faded, but these are NICMOS images, near infrared of a number of protostellar T-Tauri disks. The bright regions are mostly scattered light, scattered near infrared light, and you see dark bands in some cases, which indicate the disk proper. Now, everybody knows that, so when I say protostellar disk, I am talking more specifically about the disks around classical T-Tauri stars. So stars of roughly a solar mass, in a stage of their evolution where we can see the optical photosphere of the star, but we also see excess emission in the infrared, which is coming from the dust in the disk. Okay? So, as we all know, these disks are dusty. They probably have about the same proportion of their mass in solids as the interstellar medium, but the size distribution of the dust is very clearly different, and that's one of the great difficulties in this subject. And the disk itself in this phase is typically something like 1% by mass of the star. So the dust is 10 to the minus 4 of the stellar mass, with considerable variation. They are cool. It seems that, well, it depends what altitude you talk about in the list, but if you talk about the bulk of the mass, or the regions near the midplane, or the infrared visible surface, the temperature is probably not very different from what one would calculate by that freshman exercise of equating the irradiating stellar light to a black body, a radiator that radiates the same energy as it receives. So at 1 astronomical unit, the temperature in these disks would be comparable to the temperature in this room. And that's important to me because it means that thermal ionization is completely negligible at 1 AU. But they accrete, and we know they accrete. I won't show you the data, but we know they accrete because we observe the boundary layer emission where the disk flows onto the star. And typical rates are 10 to the minus 8 solar masses per year, but if the observations are correctly interpreted, with a considerable variation. Okay. As I already said, we see these disks mostly through their dust, but increasingly in recent years also through their molecules. And two particularly dramatic examples of this were published last year. Altogether, grand total of 3 Titari stars are represented here. So the group on the left, Carr and Ajita, published a paper in Science, Spitzer IRS observations of AA tau, which is a reasonably typical Titari star, or so they described it. It actually has a bit of a personality of its own. The disk apparently extends down to the magnetosphere, and there's an 8-day modulation of the light curve, which is thought to be due to warping of the inner disk, probably produced by a misaligned dipole. But anyway, a typical accretion rate, maybe slightly on the low side. Now, these lines, so a few of them are labeled, identified, but the vast majority of them, the unidentified ones, are water lines, or so these authors conclude. These lines are not resolved. The resolution of IRS, lambda over delta lambda, is about 600. So, and you would need 10 to the 4 just to resolve the orbital velocity if this is coming from 1 AU, which is what they conclude. But from the relative excitations of the lines, one can, and they don't explain this in any detail in their paper, try to estimate the temperature of the gas, which is emitting these lines, and also the degree of the column density from the amount of saturation of the lines. Stronger lines are quite saturated. And then from those things, the emitting area, and if you take the square root of that, you get a rough estimate of the radius from which the emission comes. Not only are these lines not resolved spectrally, they're not resolved angularly either. So the inference this is coming from a couple of AU is indirect. The temperature is rather high compared to what I just told you. If you take the column densities, they, lovely, they infer, and you assume, but both for water and for CO, which is another major constituent here, which they infer to be about equal, and you assume that the solar abundance of oxygen and carbon is locked up in these molecules. You need only a total column density, mostly in hydrogen and helium, of course, of order of 4/1000ths of a gram per square centimeter to explain this. So we're not talking about, for comparison, at 1 AU, the total column density of the disk is probably more like 2 kilograms or something. The second group observed 2 Titari stars, which were selected for having high accretion rates, high but variable in the case of dr tau, on this order, an order of magnitude bigger or more. They actually also had IRS spectra, which I'm not showing you for want of space. But they then also observed the same systems with near spec on Keck. And then they were able, in the 3 micron region. This is in, between 10 or 9 and 30 something here. Here they're about 3 microns. And this gas is hot enough, in their case, both of these systems around 1,000 degrees, that they're able to see water lines and resolve them marginally. And they interpret the widths as Doppler widths associated with the orbital motion, about 30 kilometers a second. Hence, this is coming from about an AU. Similar, slightly higher temperatures, similar column densities of water, higher column density of CO is inferred. So then you need a minimum column density about 10 times higher, but still very small compared to the total of the disk. You're popular. Now, I think the conventional interpretation, and I don't necessarily disagree with it, is for this hot material is that it's not directly to do with accretion. So the aspect. So this is these are models made with a code called ProDemo, advertised in this paper by Wojtke et al. This year. And what's plotted here is well on the axes radius logarithmically, and then altitude. I guess in this plot it's in altitude directly in AU, and in this plot it's altitude divided by radius. And the color scales are temperature and density. And although you can't see it very well, in the right-hand plot there's a dashed contour which encircles the region where the gas is 1,000 degrees or higher or hotter. Now, why does it get so hot in these models? These models, this is not heated by accretion, as I said. It's heated by UV light from the star 10 to the minus 4 or something of the bolometric luminosity goes into UV, and then photoelectric heating of the gas up here heats it up, and because the gas is so tenuous, this is well above the midplane of the disk, it can't cool very easily. So it gets hot, very hot. You know, it might be, this is 1 AU, it might be 200 degrees at the midplane here, and up here it's 1,000. But if you read off this chart, I know you can't, but number densities are shown here. So this 1,000-degree contour is at a number density of about 10 to the 8 per cubic centimeter. And if you just multiply, and then it goes down, if you just multiply that by the height, you estimate a column density here, which is 10 to the minus 4 or something. So there's not really enough of this hot gas. Also, the amounts of water relative to other things are higher than predicted by these models, at least for the Carr and Ajita observations. So there's some mumbling about, in those papers, the observational papers, about vertical mixing, and I don't know. So I think we don't really know quite what's going on. I want to suggest that maybe the accretion has something to do with this. All right. Dust. Dust does not get a good press. It's used as a metaphor for humility. I have an amateur interest in Latin, and those of you who share the same vice, I know that humility comes from the Latin word for dirt. So dust. So no, not an accident. But dust is important in astronomy for all of these reasons, and I'm particularly going to focus on the first and last group, the importance of dust for the opacity of disks on the one hand, and for the electrical conductivity and therefore coupling to magnetic fields. Now the other major dramatis persona, I guess, is water in this story. So here's most of what I've learned, not quite, but about water in the course of this study. Okay? It's a common molecule. And importantly, unlike carbon monoxide or carbon dioxide, it is not a linear molecule. It's triaxial. That means it has 3 unequal moments of inertia, which very conveniently are nearly 1, 2, and 3 in units of 10 to the minus 40 dynes per centimeter squared, which is roughly, this is roughly what you get from 1 proton or maybe 2 protons times an angstrom squared. Okay? This unit is a picometer. It's 100 picometers is an angstrom. So it's the size you would expect. The moments of inertia are about what you would expect. The bond angle, I can't explain that. I haven't learned that yet. Sorry. So it's a relatively low moment of inertia for its size because these hydrogens are light. But it's triaxial, so and therefore, if you modeled this classically, if you did the thermodynamics of this, or the partition function of this classically, which I have done, it's a little exercise, and turns out agrees with the explicit calculation, summing over the various energy levels, the actual quantum mechanical energy levels, agrees to a few percent, as long as the temperatures are less than, I don't know, less than 1,000 degrees, or certainly less than 600. Okay, so it has far more, the point is, because it's an asymmetric top, it has a lot more rotational levels than a linear molecule. And then, therefore, a lot more transitions, every pair of, not every pair, but because the angular momenta have to differ by 2 and so forth. But you get a number of transitions, which goes like the square of the number of levels. This partition function, of course, gives you a rough idea of the number of levels that are excited at a given temperature. Okay? And then square that roughly to get the number of lines you have to worry about. So, and it has an electrical dipole moment, 0.86 dBi. I didn't really know what a dBi was either. I'd heard it before, but for your education, those of you who aren't in this business, the unit is 10 to the minus 18 in Gaussian units, but what that really means is 4.8 dBi is 1 electron charge at a distance of an angstrom. Okay. All right. So I think I said this in part already. The properties of the dust in these disks can be inferred in 2 very different ways. One, by trying to model the emission. the broadband infrared spectral energy distribution, but also features that one sees that indicate the presence of silicate and other minerals. And then PAH bands, polycyclic aromatic hydrocarbons, indicate very small flakes of graphite with some hydrogens attached. These features aren't seen in all T Tauri disks, but it seems to be largely a function of sensitivity. They're present in tens of %. All right, so you model all that. Or if you're someone who worries about turbulence in disks, you try to constrain the dust by its effects on the conductivity of the gas, and you require that the conductivity be sufficient for coupling. So the idea of this project was to try to combine these sets of constraints and see if they were in conflict or to what extent they controlled the parameter space. There are, unfortunately, it's complicated because many aspects of both the micro and the macro physics are quite uncertain. And the uncertainties in the grain physics, particularly the grain size distribution, how that's maintained or how that evolves, is perhaps the most important reason for undertaking a project like this, because I don't think we're going to be able to solve this by pure thought for a very long time. Okay. Now, there is no doubt, as I already said, that the size distribution of the dust particles is very different in protostellar disks from what it is in the interstellar medium. In the interstellar medium, the largest grains are roughly 1/4 micron, with a power law distribution of sizes extending downward from that size down to PAHs, which might be tens of angstroms. From sub-millimeter wave observations of T Tauri disks, we know that there are grains present which are as large as a millimeter, maybe even a centimeter. And most of the mass is at the top end of the size distribution. So relatively little mass in the small dust. But as I'll tell you again later, for the conductivity, what matters is not the mass in dust, but the surface area. And all the surface area is at the low end. So the important question for conductivity is how much small dust is there? And that's very hard to constrain very well from the emissions, except where we do see PAH features, then undoubtedly they're very small things. But unfortunately, because we don't have angular resolution, it's rather difficult to know what radius these PAH features are being formed. And some of the data suggests they're being formed out at 10 AU or more. Because you remember that the characteristic wavelength of the emission of a PAH molecule doesn't depend upon its distance from the star. It depends only on the color temperature of the star, right? Because it's a single photon heating and then radiation. So some of the indications include modeling the so-called flat infrared spectra of disks. So this plot is usually made the other way around by observers, but these people were theorists. So we have optical wavelengths up here, okay, and radio wavelengths way down, or very long wavelength infrared down here. So this is the stellar black body. I mean, they literally clearly use the black body. That's not an atmosphere model. And what you see, the points are real data for a particular system. A lot of emission at long wavelengths. And this indicates the presence of a disk. This is how disks were originally recognized around protostars. But the flatness, the constancy of flux with frequency is a little hard to understand. If you had a perfectly flat disk re-radiating the light that was intercepted from the central star, the temperature would fall as r to the minus 3/4. And the same scaling would follow if the disk were self-luminous, if it were a traditional steady-state thin accretion disk. But this is more consistent with temperature t to the minus 1/2 or something. So these authors propose that part of the explanation, as many people said, is that the disks flare, and so they intercept more than a flat disk. Large radii in the disk intercept more flux from the star than a flat disk would. But that alone is not quite enough to explain this, and they appealed to the small grains, grains that is substantially smaller than the wavelength at which they're re-emitting over 2 pi. And so, as is well known in studies of interstellar grains, or as you would recognize thought about it at all. The temperature, in equilibrium with the radiation field, the temperature the grain reaches is determined by the optical flux that it absorbs, but also by the ratio of the emissivities at the optical, where it absorbs, to the infrared, where it re-radiates. And if this is a large ratio, then this temperature is higher than the equivalent temperature for a black body. So that's one indication. And the other indication, comes from these silicate features around 10 microns. So this is taken from a review article in the latest Protostars and Planets. And this is for different types of stars, actually. These are Herpig AE stars. These are Titari stars, which are raining. So these are brown dwarfs. And these are, you can't read it, but this is amorphous olivine in the lab for 10th micron grains, and these are progressively larger grains of amorphous olivine. These last two curves are for crystalline silicates, phosphorite and enstatite. And the general trend is within one composition, as the grains get bigger, the features get weaker, simply because the grain becomes optically thick at all wavelengths, and then it radiates like a black body everywhere and has a sort of wavelength-independent emission. So in some of these systems, these features are quite weak, and so that indicates either that the grains are big or that they're just, well, I guess it indicates that they're pretty big, yeah. Or that there's a lot of amorphous olivine doesn't dominate. But in others, it's quite a strong feature, which indicates you have substantial numbers of small grains. Okay. So I want to get through some of the topics that are laid out here. So the next thing is to remind you of the kinds of magnetic field strengths that are required to explain the observed accretion rates. And I bring this up because it seems to me already here there's a worry. I idealize the disk as a minimum mass solar nebula. Most of you know what that is. The important point here is that, again, it's cool, and it's got a column density which is roughly 2 kilograms at 1 AU, falling off as r to the 3/2. Okay. And it flares a bit. Okay. So if material is to accrete, it has to shed angular momentum. So the way that's described is balancing the advection of angular momentum inward by the accreting material at a rate m dot, mass per unit time, against a stress, which is taking angular momentum outward. And the stress, if all of these stresses are exerted within the disk rather than by a wind emanating from the disk, which is another possibility, then the stresses are of two types: Reynolds stresses associated with velocity fluctuations, and Maxwell stresses, as they're called, associated with magnetic ones. If magnetorotational turbulence is dominating, then the Maxwell stresses are believed to be bigger, so I'll ignore the Reynolds. This much than greater than really means by a factor of 4 or something. Okay, so you know how much angular momentum, what torque basically has to be exerted by these stresses at each radius, and you work that out. And so the torque involves an off-diagonal version of the stress, so you do sort of Cauchy-Schwarz, and you get a minimum field strength, which is like, well, it would be like 1 Gauss for 10 to the minus 8. And I scaled this by 10 to the minus 7 because that second pair of systems that I talked about that showed water lines had higher than average accretion rates. And because it makes things more dramatic, okay, it goes as the square root of the accretion rate. This should have been m dot. Okay, 3 Gauss. Well, that does, is that a big number or a small number? So one way to think about that is to compare the pressure of the gas to the pressure of the magnetic field. Now, now the pressure of the gas depends upon where vertically this accretion is occurring, and for reasons that I'll explain more in a moment, it's thought that the accretion is occurring largely at 1 AU at any rate, near the surface layers of the disk, layers whose column is much larger than what we talked about for those water molecules, not a fraction of a gram per square centimeter, but maybe 10. That would be a reasonable unit. 10 out of 2,000 grams per square centimeter. So if you try to force this much accretion through that column, and of course it's going sideways, inward radius, the magnetic and gas pressures are about equal. And that's for the minimum field strength you can get away with. So right away, one has to wonder, can MRI really do the job?
So this is basically just alpha of 1. That's what you're pointing out.
Yeah, that's right. If you want to do, if you want to achieve this accretion rate through only, if you do it through the, if this accretion were occurring through the entire column of disk, you could divide this by 20 or something. Okay, it would be a reasonable alpha. But if you have to do it in 10 grams per square centimeter. Also, if you reduce the accretion rate, it's linear now, the accretion rate. So if you reduce it to 10 to the minus 8, it goes down to a tenth, which is maybe not so bad. But there are these systems which accrete at very high rates. Well, so I'll get to that. That depends on the dust. So how much ionization do you need for good coupling? This is a complicated story, and I'm going to skip through it very quickly. There's more than one dimensionless parameter you need to consider. The current wisdom is that you should focus mainly on this one. Now, this number is called many other things in astrophysics, but the proper term for it, pay attention, is given by geophysicists who first talked about this combination term in connection with the Earth's dynamo. It's called Elsasser number. This particular combination of, so what you have here, b squared over 4 pi rho is basically the square of the Alfvén speed. It is the square of the Alfvén speed. And omega, of course, is the rotation, and eta is the magnetic diffusivity. So no macroscopic length is involved here. Just field strength, diffusivity, and rotation. Now the problem is, what is the diffusivity? As Mike Wardle in particular has emphasized, and others, but he's done the best job of explaining this, I think. The conductivity in these disks is non-trivially tensorial. Because typically the electrons are magnetized, meaning they execute several gyrations around a field line before they have a collision with the neutral. The ions may or may not be. So the conductivity is a tensor, and it's not entirely clear what you should use for the diffusivity, but one prescription, which Wardle usually uses, is you should use the largest eigenvalue of the reciprocal of the tensor conductivity. But what you really ought to use in the nonlinear regime in turbulence is not really known. I mean, it's easier to say in linear theory, not so obvious in nonlinear. So I'm going to just skip over that. And we're talking about, for Elsasser numbers of order 1 based on the Hall conductivity, or the Hall diffusivity, we're talking about electron fractions of order 10 to the minus 10. 1 electron for every 10 to the 10 hydrogen nuclei. And you can maybe bargain me down to 10 to the minus 12. But what we actually did in our study was not use the Elsasser number. The disadvantage of it is that it involves the field strength, so you have to. And also traditionally people have used this combination, which I don't know a good name for this, but what it's often called is the magnetic Reynolds number. So we said our condition was that this should be greater than 100. But that translates to an electron fraction about an order of magnitude smaller than what I said on the previous graph, but maybe an order of magnitude greater than some people would argue for. Okay. Never mind that. Okay. So I've said already that the accretion is thought to occur in surface layers. And the reason for this was first sort of pointed out by Charles Gamme in 1996. The temperature is much too low for thermal ionization. We do not worry about the coupling of the atmosphere to the Earth's magnetic field, at least not in the troposphere. Okay? And so you need non-thermal ionization balance. So you have to know explicitly the sources of ionization and the sources of recombination. In this paper, Gamy assumed ionization by cosmic rays, for which he took the then standard interstellar rate of 10 to the minus 17 ionizations per nucleus per second. It could be higher or lower in two-hour disks, and recently the standard rate has been revised upward by about an order of magnitude. Anyway, that's what he took. And then he acknowledged the difficulty with grains, but decided to ignore them and computed the ionization fraction that way. And the result was, in his simple estimates, was that at small radii, less than 1/10 of an AU, the whole disk was sufficiently ionized by ionizing sodium and potassium and other alkali metals to be well coupled. But beyond that radius, the regions near the midplane, which contain most of the mass but not most of the height, were relatively uncoupled, incapable of turbulence, and accretion had to be occurring in these surface layers, which are quite thick geometrically but not very thick in mass. And for him, they had a column of something like 100 grams per square centimeter, that being the penetration depth of a cosmic ray. Since then, the thinking has been that cosmic rays are probably less important than X-ray ionization, because we know the X-ray luminosities of these stars, and one can calculate its effect on the surface layers of stars. So this was first sort of done thoroughly by, again, Glassgold in a couple of papers. This is the second. And this, you probably can't read it, but this is the effective ionization rate as a function of column, not in grams, but in numbers per square centimeter, at different radii. And if you focus on 1 AU here, the ionization rate due to X-rays is extremely high by comparison with 10 to the minus 17 anyway. Near the surface at 1 AU, it's more than 10 to the minus 12. But as one goes down, so here's 10 to the 24 atoms per square centimeter. So this is about column density about 1. It's already down to 10 to the minus 15. And then it drops as you go to a few grams or 10 grams. It just drops off a cliff. It depends upon somewhat on the energy of the X-rays, or the temperature of the stellar X-rays. There have been a lot of studies of the conductivity of these surface layers, and we hope that ours is the latest and greatest, but it's surely not the last word. And I won't take you through these. Many of them ignored grains altogether. Some of them, our work is mainly an extension of the most recent stuff by Ilgner and Nelson, with an even more up-to-date and extended chemical network than theirs, and a greater exploration of grain properties, but the same general approach. I should perhaps just call attention to this parameter F, which will appear later. This is the fraction, this is the dust mass fraction in the active layers, not necessarily in the whole disk. We think that's about 1%, but in the layers that are accreting. Okay, so 10 to the minus 2 would be the interstellar value if the dust were well mixed, and anything less than that implies that grains have settled out or something. Okay. Okay, so we do all these things. We vary various parameters to see what sort of active layer we can get. And so the active layer, defined in the way I explained as having a magnetic Reynolds number of greater than 100, is extremely sensitive to the grains, and especially to small grains. So this is a very busy plot, but this is the column density of the active zone on the vertical axis. This heavy line is the r to the minus 3/2 power law for the minimum mass solar nebula. The dot dash line is what you get for our standard parameters, but without grains. Standard means, well, you can ignore the first line because there's no dust in that curve. No cosmic ray ionization, X-ray ionization of 5 by 10 to the 29 ergs per second coming from the star, and a temperature of 3 keV. Okay, and so that gives you, at 1 AU, a column of something like 40 grams per square centimeter, which is more or less in line with previous studies. But once you put grains in, let's say you put in 10th micron grains, which would be a sort of median by mass value for the interstellar medium. And if you put it in at the full mass fraction, 10 to the minus 2, you get this line, which is a bit less than 2 grams per square centimeter. So now you start playing with these parameters. You can jack up the X-ray luminosity or the cosmic ray luminosity. Cosmic rays help you mostly at larger radii. Right, they can go right through the disk. They don't help you much at 1 AU unless yeah. Well, you can make you can reduce the grain mass fraction, and so here you see curves for 10 to the minus. Here, this light solid line, all these standard parameters except the grains have been reduced by 4 orders of magnitude in mass, but still at 1/10 micron. Or you can make the grains bigger, and that helps a bit. So this is 1 micron grains, but still with a full 10 to the minus 2 mass fraction. And probably you need some combination of these in order to get up to 10 grams, okay? Or extreme values of parameters. So you can do it just by decreasing the mass fraction by 10 to the 4, as I said. That's probably too little dust in the upper layers to explain the apparent, the infrared spectral energy distributions, or even the apparent thicknesses in high resolution octave infrared observations. So probably you need some combination. And so why are small grains so important? Well, as I said, it's because the electron abundance depends mainly on total grain area. Now, I wish I could give you a really crisp physical explanation of this. I will try to give you a partial one. What do the grains do to the conductivity? Well, one effect is that electrons tend to get stuck on grains, and that greatly decreases their mobility. Suddenly this electron charge is associated with an enormous mass. But if you put 10 to the minus 2 of the total mass into 10th micron grains, you only have 10 to the 12 of them. I'm sorry. The abundance relative to hydrogen is of these 10th micron grains is only 10 to the minus 12. So if you assume you can only put a couple of electrons at most on the grains, may or may not be true, there aren't enough grains to immobilize all the electrons. But another effect grains do is to promote but if that were the main effect, what would matter is not the surface area in grains, but their number. Because you can always put at least one electron onto a grain before electrostatic repulsion prevents you from putting on another. Anyway, so if that were the main effect, it would be just grain number that mattered. And in some parameter regimes, well, we never see that, actually. That would be very dominated by the smallest particles. But also grains, as grains reside temporarily on these surfaces, they have an increased chance of encountering a positively charged ion, which also comes on the grain. So they promote, just as in a catalytic converter, they promote recombination. In particular, in a totally grain-free environment, a major source of electrons is what are gas phase metal ions, magnesium or iron, which many previous studies put in. And why are those such good electron donors? Well, it's because recombination is very difficult for a gas phase metal ion. Recombination has to be radiative. So an electron not only has to collide with a positively charged magnesium ion, it has to radiate a photon, which is difficult. By contrast, a positively charged molecular ion can typically recombine by dissociation. So you take HCO3 plus and you bring in an electron and you get something else. But it comes apart into 2 neutral molecules, and that takes up the energy. But as soon as you put grains in, these metal ions can recombine very quickly on grain surfaces. And so they make the gas phase metal abundance makes almost no difference once you have grains in the problem. Okay. Well, dust. I see your eyes glazing over, but it's good stuff.
And the photoelectric emission is lower. The photoelectric emission, production of free electrons by photoelectric.
Yes, probably because maybe in the top gram or something per square centimeter. Well, I'm sorry. Oh, you mean from the X-rays? Well, it's a source of electrons, but since there's 100 times as much hydrogen, that dominates. The higher Z atoms are important for the. Sorry. So the way the X-ray comes in, it ionizes not just one hydrogen, so it makes a fast electron, and that does secondary, and then it keeps going, and it ionizes more, and so. I'm sorry, the electron goes on and ionizes more, and you get a cascade. So you get many electrons worth out of a single X-ray. If it hits a grain, I think you typically get somewhat fewer. So I believe it's the ionization of hydrogen and helium that dominate. Anyway, if you didn't have grains, you'd still have the same high Z atoms. They would just be distributed in the gas phase. So putting them in the grains doesn't really help you in terms of the ionization rate. Okay. So again, the way we mostly know about the dust is directly through its infrared emission, through its opacity. And so you can go to Bruce Strain's website. You can make your own personal favorite mix of grains, compositions, and size. Well, he only gives you a choice of 2 compositions, silicate and iron, but then you get to integrate over different size distributions. And you can work out the opacities. And if the grains are small compared to the wavelength at which they're trying to emit, it's only the total mass of dust that matters. But if you start making the grains at 1 AU bigger than a micron or a couple of microns, the opacity starts to go down, because now 2 pi times the grain size is starting to become comparable to or larger than the wavelength that they're emitting. And so you're only getting the benefit of the surface area of the grain in the emission and not the whole volume. Okay? Right. So if the only thing that mattered for emission, for the infrared emission and for the conductivity were the amount of dust, then we could directly compare the constraints from the emission to the conductivity. But unfortunately, there's this additional free parameter, the size of the dust or the size distribution, because conductivity depends mostly on surface area, and the emission depends mostly on mass, at least until the grains become quite large. All right, heat. The disk, this accretion releases energy. That's why disks are luminous. Now, T Tauri disks are luminous mostly because of reprocessed starlight, in contrast to AGN disks or your other favorite sorts of disks. But the emission due to the accretion, particularly at these high rates, is not completely negligible. So the effective temperature at 1 AU would go like this. This is the 4th root of the accretion rate. Now the actual temperature is higher, of course. This represents the flux that's coming out. Now this has to be radiated somehow, and normally you would assume that it's radiated by dust, and it probably is mostly, continuum emission by dust. But if you deplete the dust enough, for example, in one of those curves for the column density of the active layer, I talked about a dust mass fraction as low as 10 to the minus 4 of the interstellar value. There would not be enough continuum opacity in the dust to radiate. And so the gas would have to get quite hot compared to this effective temperature. The gas temperature would have to go well above the effective temperature in order to radiate the heat of accretion. And other sources of opacity, particularly molecules, might become important. Okay. Okay. And the point is that depending, and I'll make this more quantitative in a moment, on exactly what you assume about sizes, the optical depth of this active layer may have to be less than 1 in order to allow the layer to be conductive enough to be coupled. It's just on the margin. Okay. Almost all of that work that I described was actually done by my collaborators running by, who went back through all these previous papers on the conductivity and went into the UMIS database, the latest version, and got all the chemical reaction rates and did the integrations with guidance from me, but he did all of the dirty work and made those complicated plots. The part that I actually did myself is this molecular cooling. And I only just scratched the surface. But just to remind you, since we're so concerned with greenhouse warming these days, global warming, the main greenhouse gas in the Earth's atmosphere is water. CO2 is of secondary importance, but we're not changing the water column nearly as much as we're changing the CO2 column in logarithmic terms. And since the temperatures in protostellar disks at the regions we're concerned with are similar to the temperatures in the Earth's atmosphere, chemical equilibrium, not surprisingly, although the densities are quite different, gives you abundant amounts of these same molecules. Okay. However, molecular lines are much less effective as opacity sources in protostellar disks than in the Earth's atmosphere. And the reason is pressure broadening. Okay? So you have a molecule in some excited state, and it's waiting around to radiate its photon at the rate that you would calculate from, Fermi's golden rule and the overlap between two states or something. But before that happens, it gets hit by another molecule, and it doesn't necessarily radiate, but its phase gets interrupted. Okay, and so the line is broadened by this. Okay, and in the Earth's atmosphere, the pressure broadening is about 100 times larger than the Doppler broadening due to the thermal velocity of the molecule. And there are a lot of lines, and some of them are quite strong. So you broaden. So if they had only their natural widths, or their natural widths plus their Doppler widths, they would be extremely strongly saturated, and they would block the infrared light in a small part of the spectrum, but most of the spectrum between them would be clear, and the heat would escape. But or the opacity, the mean, the Roscelin mean opacity would be small, or even the Planck mean, because of the saturation of the individual lines, would be reduced. And that's what happens in protostellar disks. But in the Earth's atmosphere, because of pressure broadening, they overlap a lot. Oops. Unfortunately, pressure broadening is not terribly well understood or described. But fortunately, in protostellar disks, it's small enough that you can pretty much ignore it. Some lines are so strong that their extreme wings have to be taken into account. So what you do is you find some database of water lines, and most of these are calculated, not measured. There are far too many of them. So I used the Barber and Tennyson one, which has 28 million lines or something in it. Most of them at excitation temperatures that are too high to be important, but what the hell, you can sum over them. And this is a tiny piece of the spectrum. This is a frequency in the units spectroscopists like to use, inverse centimeters. And this is the cross-section per molecule as a function of wave number on the vertical axis. And the blue dotted dashed line I've drawn in here is the level at which the line. So these are the unsaturated line strengths, as if you had a very, very small column density of water. Any line that pokes up above this blue line would be saturated if you had 10 grams per square centimeter at solar abundance with all of the oxygen in water. Okay? And then down here, you can see the Lorentzian wings from collisional and broadening and the natural widths. The natural widths are totally negligible. It's collision. After Doppler broadening, it's collisional broadening. Okay. Okay. So to calculate the emission by molecules, you have to do an appropriate weighting of this spectrum, taking into account saturation and acknowledging all these gaps. And so if you do that, never mind the details. So I don't know why people don't, plot things this way. They always show you spectra. The strength of the line is a function of wavelength. But when the spectrum is that sparse, you should plot the integral of the spectrum. This is what mathematicians do when they're trying to define, you have some irregular, the integral of an irregular function, like a function which is 1 on transcendental numbers and 0 on rationals. It makes no sense to plot the function, but you can plot its integral. So that's what I've done here. For different assumed temperatures and column densities. Okay, and so the emissivity, this is the cumulative emissivity. So you integrate the total amount of emission, and you normalize by what a black body would emit. Okay, and you see it's quite small, but it's much more sensitive to temperature than it is to column density. Because the column density affects only the saturation of the strongest lines, and logarithmically, the temperature affects the Doppler widths. And if you double the Doppler width, you get twice as much absorption out of one of these strong lines. So the bottom line is you typically get emissivities of something like 10 to the minus 2 out of water. Okay? So in order for molecular emission to dominate, you have to reduce the dust opacity to about 1%, or else raise the temperature, considerably. If I didn't go all the way up to 1,000 degrees here, but I guess it would be about 10% if I did. Then you only need to reduce the dust opacity to 1/10. So for molecular cooling to dominate, you need an extreme reduction of the dust with this line is, let me just as an aside. If you were to simply sum over the line strengths and ignore saturation, the Planck averaged opacity would be 8 centimeters squared per gram, which is quite large. So the fact that this is so much smaller is just a reflection of saturation. Okay. Oh no. Well, a critical plot has, okay, I have to open a different file. I wish I could. There's a not quite correct version of this plot. My PowerPoint crashes on this machine from time to time, taking with it usually the most complicated slides. Okay, so this is a not quite correct, older version of this. All right, so, okay. So this is an attempt to combine the constraints from, as we understand them, from emission and from conductivity as a function of grain size and dust mass fraction on a single plot. Okay, so the horizontal axis, we were talking about a single population of grains. This is just the size of that population. The vertical axis, dust mass fraction. So for interstellar dust, if you were to represent it as a single population, a crude representation, it would belong here in this plot. If you have an extended power law MRN distribution, then this represents the upper size cutoff in that power law. We take the minimum grain size to be 10 to the minus 2 microns in all cases. Okay? All right. So below this thin solid line, you can get an active surface layer greater than 10 grams per square centimeter at 1 AU. And so either you make the grains big, or you make the mass fraction small, and you stay under this curve. If you have the extended, if you have a power law distribution extending down to 0.01 microns, you have to be below this line. So the difference between these two reflects the importance of the small mass but large surface area in the smallest grains. All right. Now, these loci here for different temperatures are the loci at which the continuum opacity in dust is equal to 1 for various temperatures. It doesn't depend much on temperature for single-sized grains. So what you can see is that as you make the grains bigger, their effect on the conductivity is less, so you can tolerate a larger mass fraction. Presumably, you wouldn't go above the interstellar value, so this is kind of notional. But you also make the optical depth in the infrared, the infrared, not optical depth, smaller because you're making the grains bigger and their optical efficiency factors are going down. And remarkably, the two sort of track each other, which means that for single-sized grains, if you just marginally satisfy the condition for good conductivity, you're getting an optical depth of order 1. Now, because of all these holes between the water lines, at optical depth 1, the dust still overwhelmingly dominates the cooling. But there's a possibility of seeing the emission lines from the active layer. Because the optical depth is, if continuum optical depth is much bigger than 1, you won't see the you won't see the molecular lines. And these, yeah, that's for power law lines. Okay. And these red lines are the loci at which the molecular cooling actually dominates. Okay. So if you had, and again, as far as cooling is concerned, as long as the grains are smaller than a micron or something, or even 10, well, the cooling doesn't depend much on the sizes of the grains, just on their total mass, the dust cooling. But if you were to take this MR size distribution, which is empirically a good description of interstellar dust as far as we know, and also, as Hilke will tell you, I think, this index is something that seems to describe the size distribution of much larger bodies in the solar system. It's a natural value for a collisional cascade. Whether that has anything to do with dust, I don't know. But, so if you were to adopt that, and hence have some really small grains around, you would probably be in the situation where most of the cooling would actually have to be molecular.
Consistent with the luminosity of the lines? Is that consistent with the luminosity of the lines? You have an accretion rate and the line is
Good question. I don't think so, for those systems that were observed. I mean, there are very few observations yet of these systems, right? So, I mean, on the one hand, the total emission from those lines is more than you can quite explain from the UV from the star, but it's, on the other hand, it's less than you would get from if that were all of the accretion energy. So presumably the truth is somewhat in between. So now, if I can go back to the other, cancel. No, I want. Nope, I do want this. So I'm basically done, actually. I'd be relieved to know. So I tried to tell you a lot of little pieces of physics that I've learned along the way, which are standard pieces of physics, but may not be familiar to all of you. The pressure broadening, the metal ion story, the magnetic field limits. But the main scientific conclusions of this study are as follows. You need rather strong fields to explain accretion at values as high as 10 to the minus 7 solar masses per year, is sort of the upper envelope of what you see for T-Tauri stars, in the minimum mass solar nebula, unless the surface density of the active layer can be substantially above 10 grams per square centimeter. We tried very hard to make it bigger, but it's difficult unless you depart considerably from standard assumptions, or unless we're making some fundamental mistake. But as I said, our results are pretty much in line with previous ones when one includes all the physics that we included. In other words, when you don't neglect grains and so on. So, a best bet would be you suppress the grains by something like, the small grains at least, by something like 10 to the 4 compared to their ISM values. Either by having a lot of dust settle or by having much of it go into bigger grains. And in that case, the active layer should be at least marginally optically thin. So in answer to the previous question, my guess, based on the limited data available, which I have not explicitly modeled, I have to confess, I'm looking for another student to do that with, is that we're in this intermediate regime where the active layers are somewhat optically thin, but the cooling is still mostly coming out in the continuum. So you'll see these lines. The lines will have a good line to continuum ratio contrast, but they won't dominate, they won't carry most of the heat. Oh, this is the wrong version of it, isn't it? No, it's gone. Well, it's here somewhere. Okay. I think I'm going to switch to Keynote. So there's no. All right. There was supposed to be another bullet here. I don't know what it's done to me. There's a possibility, it seems to me, that we are actually missing some important source of ionization. You would only have to put something like 10 to the minus 4 of the accretion energy into non-thermal particles, or X-rays, in a corona to compete with the X-rays coming from the star. Because the accretion luminosity is down by only an order of magnitude or something compared to the intercepted optical light. But the X-ray flux from the star is only 10 to the minus 4 or something of its bolometric. So a local source of energetic particles or X-rays coming from the corona of the disk would help a lot with the ionization. In this way, the MRI could sort of pull itself up by its own bootstraps. And the question is, is that possible? Have we overlooked a major source of non-thermal ionization? Secondly, I think the people who do these simulations, who tend to use very simplified physics, isothermal equations of state and things like that, maybe diffusive radiative transfer, but usually none, need to start getting a little bit more serious about the microphysics. I mean, it would be nice to know what is the temperature structure of these active MRI active layers. The simulations that I've seen typically show that most of the dissipated and the scale height of the energy dissipation in magnetic turbulence is larger than that of the gas, so that much of the energy gets deposited in low density regions where it might be more likely to make interesting emission. And the hope, of course, is that if you do enough of this modeling and compare with the observations, which I think are going to exponentiate in the future of these molecular lines, you'll actually be able to constrain the very difficult physics in these dusty layers. I mean, I think this is a more difficult problem than AGN disks, frankly, because the microphysics is much more uncertain. Okay. And just the last possibility I wanted to mention. The magnetic fields are problematic, so you might ask, is there any other way to drive accretion? And the best alternative seems to be magnetized winds. And a simple argument along the lines of the ones that I gave you for the field strength required for turbulence tells you that in principle you could drive the accretion with a weaker field in a wind, weaker by roughly the square root of the thickness over the radius, or in the stress, just the square of this, simply because there's more surface area available at the surface of the disk than there is across its thickness. But I don't know of any explicit wind solution which accomplishes this with a weaker field than you would need for MRI. The ones I am aware of, Mark Wardle and Eric Kernagel and collaborators, ones they come up with typically have stronger fields than what you need for MRI. So, and then you have to explain how the field gets to be that strong and so on. Okay, so that's it.
In addition to additional sources of ionization, one could principle of the clumpy distribution of dust. So that the patches of the disk which are very dust depleted and MRI active, and the magnetic field is when resistive layers separate them, but locked into the ionized patches.
Yeah, that would have some implications for the SED, I would think.
Well,
I'm not saying it's in contradiction with what we know.
As long as the individual dust patches are themselves optically thin, you won't change the column through the dust.
Oh, if they're optically thin. I thought you were
Nope.
going to make them optically thick.
Well, the whole layer is
Oh.
optically thick, right? But as long as the individual dust patches, clumps are optically thin, you won't
Oh, I
change
see.
the individual.
Oh, I see what you're saying. Yeah, very small scale clumping.
It doesn't have to be that small scale.
Yeah, I don't know. Well, that's certainly a logical possibility. Offhand, I'm not sure how I would segregate these, 100th micron grains from the gas, because they're pretty tightly locked, but maybe there's some way of doing it.
So if you have 100 micron grains,
100 or 100th?
100 micron grains,
Yes.
your plot is showing you can have a dust mass fraction comparable to the standard value. Is that right?
Yeah, well, was it that large? But yeah, something pretty big.
And the curve is bending up to the right.
Yeah, it's in the other version of this talk.
And then at some point, for temperature of 200 degrees, the opacity starts dropping. And
Right.
That's what, about 30 microns or 10 microns?
The opacity starts dropping actually at a few microns, the infrared opacity. That's that plot. Actually, you can see it there. Okay, so what are we looking at? This is the, so at 300 degrees, yeah, so as you go, at 10 microns, it's already dropped. These other curves are pretty much clustered together. It's not monotonic because
That's for a single grain or for power?
this is for
I see there's both on there.
yeah, that's right. The dashed is the power law. The colored curves are single populations running from 100th of a micron there to 30 microns here. So the big step seems to be between about 3 microns and 10.
So yeah, so a couple of relevant issues to address either one or both. If you're accreting through these active layers, you expect the accretion rate m dot to be independent of radius, so it can build up mass for effective diversity phenomena. And makes the other issues in terms of getting dust grains out of this active layer, you sort of have a trap over it, where it's the dead zone is really dead. Once dust gets in there, to some extent falls down, doesn't lift back up. So how effective can it be?
Well, on the first issue, I mean, this was one of the points that Gamy originally made. Yeah, I agree. There's no particular reason that the accretion rate should be constant with radius. And so I guess you could say the fact that the accretion is at the moment at the boundary layer, say 10 to the minus 7, doesn't mean that it's 10 to the minus 7 at 1 AU at this moment. You have to, but yes. But at some point it must have been. So I guess you could have a situation in which the disk bursts up to 10 to the minus 7 without ever having an accretion rate that high in the regions where there is an active layer. So the systems, if you select systems for high accretion rate, you may be misleading yourself. Fair enough. But already 10 to the minus 8, it's slightly uncomfortable. The second issue, trapping dust. Well, I mean, this is an example of just many uncertainties that you face when you try to model the dust by pure thought. Another one is, what should be the evolution of the size distribution? So people who think about this, like Dudemel, can construct models in which the dust agglomerates up into large bodies in 10 to the 4 years. You know, if you assume good sticking or something. But in fact, if that were the case, then in these disks we wouldn't see any small dust. These systems are typically hundreds of thousands or millions of years old. And as a matter of fact, that review article from which I stole that plot of silicate features makes the point that although we see evidence for large grains and small grains in many different types of disks, many different T-Tari disks, we cannot construct a chronological sequence. That is to say, if you try to date the disks by dating the protostar on some protostellar evolutionary track, there is no good evidence that the grains get progressively larger with time. We believe that on the basis of theoretical prejudice, but we can't demonstrate it yet from the observations. It's as if those large grains were there immediately, but the small grains don't go away. So there must be some sort of dynamic equilibrium in the size distribution.
What is actually the positive evidence for the small grains, the 10 to the micron grains?
Well, the evidence, first of all, there's pH features in some cases. Secondly, the evidence for submicron grains comes from this flat infrared spectra on the one hand. The silicate features probably only require less than 10 microns. So, yeah, direct evidence for 10th microns, it's a bit sketchy. Another thing we did not do in this paper is to try to repeat the SED modeling ourselves. That's another thing that should be done. Asking what is the largest grains you can get, the largest minimum grain size you can get away with. But certainly the Chang and Goldreich and other models tend to use grains that are like a third of a micron or half a micron.
Okay, if there are more questions, we'll put these upstairs. But otherwise